comments, suggestions or complaints in addition to all the usual communication channels, come and send to me.
But if it's about this lecture, first come to me. Okay, so can you hear me? Yeah? So let me now continue with what the chapter which I started yesterday on the irreducible representations of the Poincaré group, which I told you are in some sense you can take as a definition of what we mean by an elementary particle. And at the end of yesterday's lecture I said there were two, just like for the rotation group where you label the representations by the spin. There are also Casimir operators for the Poincaré group, and there are two rather than just one, and the two are given by m squared, which is clearly the mass. So there was one Casimir operator, and the other was given by w squared, w mu, where the w mu was defined as follows: epsilon mu nu rho sigma m mu rho p sigma. And Casimir means that, as you can check, this is a little exercise you can do on the back of the envelope, that both m squared and w squared commute with all the generators of Poincaré, that is with momentum and m mu nu. Now we want to analyze this a little further. Now this is obviously the mass of the system or the particle. Now what is this? Well, you can already see here that this is going to be related to spin because this has the angular momentum in it. And by contracting with an epsilon, with a p, the effect of this is that you eliminate the orbital angular momentum, which would be something like p nu x rho, that would drop out. So this will be related to spin. So this is mass, or mass squared, and this is going to be the spin. And this is already enough to classify the representations. You just have to be careful about the m squared. You have to distinguish two different cases, namely, you have to, according to whether whether you're dealing with a massive representation or a massless representation. So we know, in order to specify this a little more, distinguish between the massive and the massless case. So m squared different from 0 and m squared equals 0. As you will see there, as you perhaps know, the representations in these two cases are indeed different in the sense that the number of states you get does differ for these two cases. Well, so let's first look at this case, m squared. So m squared is equal to or different from 0. Now in this case you all know that given any 4 vector, and we assume that we're now looking at a state that on which this p mu acts diagonally, we can always switch to another frame, namely a so-called rest frame, where p mu has the following form. It's just the first component different from 0, and then there's no momentum. And as we said, we're going to assume that m is different from 0. Now, as you can see from this very definition here, you can immediately see that w, p mu, w and p have a vanishing scalar product, which means that w u is of the form where it has a 0 here, and then it has something here. Now, it's also not difficult to check. So it's a little exercise, another exercise, to compute the commutation relations of two such W's, given the commutation relations of the Poincaré algebra, which I wrote down yesterday. And then what you find is the following. You find that W nu is equal to I epsilon mu null rho sigma W rho P sigma. So these things do not form a Lie algebra in the usual sense, because for a Lie algebra, of course, on the right-hand side you would have to have again some kind of generator, but what appears here is a product of two generators. So in general, you cannot think of this as a kind of Lie algebra. However, in this specific case, you can, in fact, reduce this, and you can show that the following is true. If you define S as 1 over m times W, then you can check from this, but just by substituting here, you see that this is the only contribution that you have here is when sigma is equal to 0, then we have 0th component. And then you can check that the space components of this vector have the following commutation relations, namely Si, Sj, is I epsilon ijk, Sk. So that means that what have we found here? We have sort of extracted out of this relativistic algebra. Now by going to this special frame, we have extracted the angular momentum algebra. It's just a special case, a special frame. And if you undo this choice of frame, you can think of what you get then as relativistic generalization. So although this looks like it's only three-dimensional covariant, of course the whole procedure preserves the four-dimensional Poincaré invariance. So what is this? Of course, this is spin angular momentum, and the generators of spin angular momentum operators generate the rotation group. S generate SO3, and SO3 in this context is also called little group. Namely, that group, that subgroup of the Lorentz group that leaves invariant this special 4-vector. Leaves invariant. So this is a subgroup of that subgroup of the Lorentz group that leaves invariant this vector. So we now know how to classify the states or the representations. They are labeled by two numbers. Are labeled by two numbers, namely m squared. That's one number, and the other number is the number the spin of the state, total spin S, where of course S squared on the state is equal to S times S plus 1. So this is a very general result, and in fact, if you look at this, you can even allow for m squared being negative in principle. Normally that's not done because we require m squared to be positive, but in principle you could also take m squared negative, and then what you get is a so-called tachyon. A tachyon is a particle that always moves at speeds greater than that of light. We haven't seen any tachyons, but as a theoretical possibility, they exist not only in science fiction, but also in this representation theoretic sense. So, well, these are the labels of the representations, of the total representation, but we also want to label the states. And to label the states, and to get the most general state, we can still boost. We have to boost this back to a most general frame. And then, so to get the general state, we have to boost. We must boost. Boosting meaning you now go to Lorentz frame that's moving. And then the states are labeled by well, you have the representation label. Then, of course, even in the rest frame, of course, you still have 2s plus 1 states corresponding to this spin. And in addition, if we go to general Lorentz frame, this state will be moving with a certain momentum. So the total state can be labeled as follows. It's a particle that has mass equal to m, total spin s. In the rest frame, you look at a certain component of this spin, and then you simply boost this to a general Lorentz frame. Now, how this is done in practice, this all can be worked out in more detail, but it would take the rest of this lecture to explain how to properly define this, and you can also evaluate the action of the Poincaré group on this state. This is something you can look up in the books. This becomes rather technical, but it's all well, all these procedures are well established. So what have we learned? Indeed, this is what we would have expected anyway. Elementary particles are labeled by their masses, by their spin. And of course, there may be other quantum numbers, which we have not considered here, such as flavor quantum numbers. Now, the second case that must be considered is m squared equal to 0. And then you can see that this analysis is a little different. Namely, first of all, because in this case, we cannot go to a rest frame, but we have to go to a frame where the best we can do is the following. We have to go to a frame where the particle is moving along one direction, say the third direction, and I take this to be positive, otherwise I would have to put the modulus here. Now again, we can now exploit this relation here, but then we find that because there are now two components, we find that W mu is not of this form, but of some other form, namely W mu is equal to, well, we have something in here, we call it W1, W2, we call this W3, but if the scalar product between these two is to vanish, then we must put W3 here. So again, we have three components, just like here, but the algebra they now generate is different from this SO3 algebra. Now, again, you can evaluate the algebra in this frame, again by using this commutation relation, and then you can show that instead of the usual angular momentum algebra, we get another algebra, which is as follows: W1, W2 is equal to 0, W3, W1 is equal to IK, W2, and W3, W2 is equal to minus IK, W1. Well, what is this? Well, it's certainly not an SO3 algebra. What it is, it's an algebra of two translation generators. You can think of these like translation generators. And in the x and y plane, and here W3 is the generator of rotations in this xy plane. And this group is called little group, in this case, is called ISO2, This notation simply means that you're looking at the SO2 group, the rotation group in 2 dimensions, and the abelian group, plus the 2 translation generators. Now, if we think about the representation theory of this, the most general possibility is, of course, if this is like a momentum operator, that we have a continuous spectrum. However, in nature, the only case that seems to be relevant, the only relevant case seems to be that eigenvalues of W1, W2 are equal to 0. It could be otherwise, but such representations do not seem to, for which W1 and W2 are different from 0, do not seem to play a role in nature. And then we're simply left with, in this case, this vector becomes equal to W3, 0, 0, W3. And the SO2 group, which is left, is the one that acts on these 2 components, SO2. Well, in this case, you see that W mu is equal to some constant times P mu. They're proportional. And this component, this number here, is called the helicity. Now you see that there's now a difference. We no longer have here we have 3 operators. We have the third component, and then we have the raising and lowering operators of angular momentum to generate from a given highest spin the whole multiplet, all the 2s plus 1 components of the multiplet. But there's no such operator here, and that means that the state, now we just have in this frame, we simply have the momentum and the helicity, which is, as one can check here, in a non-relativistically invariant way, can be written as follows. This is the angular momentum along the axis of motion of the particle. So it seems like instead of 2s plus 1 components here, we have just 1 spin component. This is not quite, there's something else here, because as I will explain again, there's a general consequence of the basic postulates of quantum field theory, there's so-called CPT theorem. The CPT theorem tells us that if you have a relativistic quantum field theory that obeys all the axioms, then this theory should be invariant under the combination of 3 discrete symmetries, namely time reversal, parity, and charge conjugation. And that means if we're given a state of a given helicity, then the state that you get by applying this CPT operator to it must also be included for relativistic, to maintain relativistic invariance. Now what do these transformations do? Well, C is the operation that maps a particle to an antiparticle, and does nothing else. P, what's P do? Well, P maps momentum to minus momentum, and angular momentum to minus, and angular momentum to plus. This is a so-called axial vector. And the T, time reversal, that reverses the sign of both the momentum and angular momentum. So altogether, what do we get? If we combine the whole thing, then the CPT operator maps particle to antiparticle. And lambda helicity to minus lambda. So what this means in practice is the following. If you think about the theories that we know, for example, Yang-Mills theories or gauge theories. In gauge theories, we're dealing with a spin 1 particle. So, for example, QED or QCD. We have spin 1. And whenever we have this spin 1 particle, it means that we will have two states, provided the particle is not charged. So, for example, for the photon, we'll find two helicity states, plus and minus 1. This is well known. And as a consequence of this general analysis, we can say that we've now found on very general grounds why the massless spin 1 field, like the photon, does not have a helicity S equals or lambda equals 0 state. Well, in principle, we can now go on. We can go to spin 3/2. The corresponding field would be called a gravitino. And the theory that comes with it is so-called supergravity. There you have a gravitino, which is a particle that has spin 3/2 and helicity 3/2 and minus 3/2. So in this case, the helicity states plus minus 1/2 are missing. And we also have a spin 2. And spin 2 means that, massless spin 2 means that we have helicity plus 2 or minus 2. And that's just the graviton. And the corresponding theory is Einstein's theory of gravity. So it looks all very easy, but of course when you really try to work out the Lagrangians for these theories, it's already quite complicated for spin 1. If you go to Yang-Mills theories, non-abelian gauge theories, well, Einstein's theory was written down in 1915, but it took some while to realize that this theory just describes massless spin 2 and that there are only two physical states for the graviton. And it was only in 1960 or so that Feynman proceeded the other way. He said, let's start with a massless spin 2 particle and try to work out what its possible interactions could be. And of course the interactions must be consistent in the sense that they should not force you to introduce the lower helicity states. You see here you have already 3 helicity states missing. And by doing so, he was led back to Einstein's theory. Now, this representation theory would, of course, also allow massless field theories for spin greater than or equal to 5/2. But it seems like there are no consistent interacting theories known. Well, there are certainly none known, but it seems like they do not exist. And you can see a little bit what the problem is. Here, how do you get rid of these missing helicity states? You need, as we will see, gauge invariance. In QED or QCD, it's just an ordinary non-abelian transformation. Here, you have to get rid of 3 helicity states. That's done by general coordinate transformations. Here, you also have something. But as you go higher and higher in spin, there are more and more helicity states missing, and you need more and more gauge invariance to get rid of them. And if you try to really do it, then it seems like this is ruled out. And from what we know by just looking around in the universe, it seems like massless field theories, consistent interacting field theories, stop at spin 2. So we've reached these conclusions with, remarkably little input, because all I used here was the representation theory of the Poincaré group, and this is as much as one can say. We now want to learn more about quantum field theory. We have to be more specific. This applies to any kind of quantum field theory, whether it be scalar field theory or quantum field theory of a spin 1/2 particle. And it will also apply in some sense to, although you have to go a little further if you want to include gravity. So, next chapter will become more concrete and study a simple model of quantum field theory, namely the free scalar field. So this is chapter 3. This is the quantum field theory of a free scalar field. Well, as I said, this is not the real world, because the real world consists of interacting particles. If we were just free particles, we wouldn't even see each other. With just these free particle states existing forever. But we'll still have to look at this, because simply for pedagogical reasons, because this provides an example. A very simple example of what quantum field theory is all about. That means, in particular, we can understand the Hilbert space of the theory, and construct this very explicitly, or rather it's called Fock space. And this is the Hilbert space describing not just single particle states, but multi-particle states. And secondly, you can understand what these field operators do. So we can say something about the field operators. You can construct, you can solve the quantum equations of motion. You can understand the singularities. Short distance singularities are all previous with ultraviolet, large momentum, singularities, etc. So this is a useful thing to look at, because you can understand all these things very quickly. But it's also a useful thing to look at, because this is essentially only one theory that can be solved all the way in 4 dimensions. And it's also important because this will serve as a starting point if we want to look at interacting quantum field theories. The basic idea being that even if we look at interacting field theories, in practice the processes one looks at are processes where particles interact in some detector, say, but once they come out of the detector they behave as free particles. So there's a scattering theory that is of course not based on a free field theory, but where the interaction is localized, and in some asymptotic sense you're again dealing with free scalar fields. And of course, as I said, we cannot solve the interacting field theory, but we have one of the few ways to deal with interacting field theories is perturbation theory. And perturbation theory generally means that you start from some theory that you can solve exactly, in this case the quantum field theory of a free scalar field, and then you do perturb a little bit, and then you develop an approximation scheme where you can calculate things order by order. So this is a sort of canonical starting point for quantum field theory, or in any lecture on quantum field theory, and it would be rather unpedagogical to start with the most general case with interacting fields, because this would be very difficult. Well, so what is a scalar field? A scalar field is of course just, before quantization, it's simply a map from the 4 dimensions which assigns to every point in Minkowski space a field phi of x. And in this case, it's just a scalar, but in more general situations, we'll be dealing with vector fields. For example, if you think about the photon field, and if you're dealing with gravity, you would even think about tensor fields and all these higher spin. When you want to write down a field theory for higher spin, you would have to replace this by some tensor field with more and more indices. Well, so we have a scalar field, and what's the equation? Of course, the equation one looks at is the Klein-Gordon equation. That's the simplest thing you can do, which is box plus m squared phi of x equals 0. Now this equation has a long history. As you may know, it was invented in the 20s when people were trying to generalize the Schrödinger equation, which is a non-relativistic model of quantum mechanics, to make it relativistically invariant. And this was, of course, here you do the same thing as with the Schrödinger equation. You take the dispersion relation, in this case of a relativistic particle, and you simply replace the momentum by a differential operator, d by dx, and then you impose this as a wave equation. As you know, for the Schrödinger equation, this works marvelously. Well, people looked at this, and then they realized that there were some difficulties with that. And the first difficulty was that if you interpret this as a one-particle theory and want to apply the usual interpretation of quantum mechanics, you have to look for probability density. And it turned out there is no positive definite probability density. So there were some difficulties. Let me list them once more. There's no positive definite probability density. Well, there's a conserved there's a conserved current in this theory, if this field is complex. Namely, you can show that J mu, defined as follows, phi star d mu phi minus d mu phi star times phi is conserved. So this is conserved. This is easy to check from this basic equation. But as you can see, the probability density here, which I would get, which is J0, is not positive definite. Well, so this seems to rule out this theory, at least in the context of ordinary quantum mechanics. Incidentally, it was, it was basically this idea that led Dirac to think again about the, led Dirac to the idea that he should be looking for an equation that would be first order in the derivatives, not second order like this equation. Because he realized, and I think he was sitting in St. John's College staring into the chimney when he realized this, he realized that the reason that this is not positive definite was this derivative inside. You see, if you didn't have this and didn't have this term, it would look positive definite. And so he, a 4 vector, and then he realized that this is positive definite indeed. So that looked like good news. And moreover, what you can do, of course you can, it was clear that, as you know, that for the hydrogen atom, the Schrödinger equation works well in the first approximation, but then there are all kinds of relativistic corrections. And then you can, for example, solve the hydrogen atom, try to solve it with this equation and with the Dirac equation. In both cases, you get relativistic corrections, but then it turns out that the Dirac equation gives the complete agreement with the experiment. So it seems like this is a good feature. It seems like a good reason to abandon the Klein-Gordon equation in favor of the Dirac equation. So that seemed to solve this problem. But there's another problem now, namely having to do with the occurrence of negative energy states, or negative energies. And this is simply because the dispersion relation that follows from this is that omega, I can have plus or minus omega p, where I will use this notation in the following, omega p being the square root of, well, if I write it like this, plus square root p squared plus m squared, energy of a relativistic particle, that we can have both signs in front of here. Now that for the physics interpretation, this would be a disaster, because it would mean that you can extract an infinite amount of energy out of the system by simply dropping further and further in the energies. Incidentally, as long as you're dealing with a free field theory, this wouldn't be so much of a problem, because a free particle sits there, moves, remains in some sense it doesn't change. There are no transitions between different states. So if you put it in a certain state, it will remain there forever. So the true inconsistency only arises when you switch on interactions, because then you can think about processes whereby you extract an infinite amount of energy out of the vacuum, or you making use of this, oops. So the resolution of this, of all these difficulties, it became clear that these difficulties could not be resolved within the framework of one-particle quantum mechanics, and so these difficulties can only be fully solved in quantum field theory. And what this entails is, in some sense, that you have to go further. You have to do another step here, and this step at the time was called second quantization. Second quantization or field quantization. This is a little funny name because either you quantize or you don't quantize, but you don't quantize several times. So I don't think that people nowadays would choose to call it this way, but it has a certain historical dignity about it, so you will still find this notion. By the way, nowadays people even talk about third quantization, which sounds even more difficult to understand. But what is simply meant, or what was meant in those days, is that when you go from classical mechanics to quantum mechanics, you replace phase space variables by operators. This, in this context, simply meant that you place the momentum by the corresponding operator to get this box operator. And then this would be viewed on a par with the Schrödinger equation. But second quantization now means that we go one step further. We no longer think of this wave function as a number, a function, but we think of it, we replace this thing, which is a number, by an operator. And replace it on some operator, then of course we'll have to specify what kind of operator it is and what kind of Hilbert space it acts on. And this is what this section is about. So to repeat, if you really want to overcome these difficulties, then you have to second quantize the theory. By the way, this is also true for the Dirac equation. Dirac resolved it by this intuitive or very sort of intuitively appealing idea of a Dirac sea, where he sort of fills all the states up to 0 and then extracts particles that then will reappear as holes. But in the modern language of quantum field theory, there's no need for a Dirac sea. You just define the vacuum and you define creation and annihilation operators for the particles and for the antiparticles. So these negative energy states are associated in quantum field theory with so-called antiparticles. And that was one of Dirac's most famous predictions, as you know. So how do we quantize the scalar field? How do we second quantize this theory? Well, there's a procedure called canonical quantization that you all know from basic quantum mechanics. And this is what we're going to repeat and going to apply to this system. But before I do this, I still have to introduce a little bit of notation. The first being that we have to sort of write down what the classical solutions of this equation are. And that is, can be done very easily. We define three solutions of this Klein-Gordon equation. We just simply define them as follows. We say that it's 1 over 2 pi over... It's really not... I shouldn't harp on this normalization because we won't go into those details. It's just for completeness that I included here. Then you write this as omega of p times t minus p times x. So this is a free wave where omega p is the this energy, and then you can easily see that this plane wave solves the Klein-Gordon equation. And this is by convention positive energy solution. And the negative energy solution is the one that has minus omega p here. And so we simply take the complex conjugate, call this negative energy. So given this, we can expand any solution of the Klein-Gordon equation as follows. We can write phi of x is equal to d3q divided by omega over q times, well, we simply expand it in terms of these solutions. We write fq of x times some amplitude, which I'm going to call a of q, plus fq star of x times b of q. And for notational, it's just a convention that I call this not b, but b star. So what do we have here? This is just a Fourier expansion of this field. Still, everything is still classical at this stage. Here, I've not just written d3q, but I've written d3q divided by 2 omega of q. And the reason is simple, because this is a Lorentz invariant volume element. You see, this wouldn't be Lorentz invariant if I just wrote d3q. And the reason it's Lorentz invariant, roughly speaking, is that when you do Lorentz transformation, you have some kind of contraction or dilation, and this cancels between these two factors. By the way, when you calculate cross sections, and then you have to integrate over phase space momenta, it's always this volume element that you integrate with. So this is one reason that you end up with the Lorentz invariant answers. So this is integrated over the space of all three momenta. Here we have the plane wave solutions, and these things here are, of course, like Fourier amplitudes. They will later on become creation and annihilation operators. They can already see that this is going to be something that describes an infinite set of creation and annihilation operators for particles corresponding to or having momentum q. Well, this is now complex. You see, if A is different from B, that's complex, and so this is a complex scalar field. and a real scalar field is obtained for by setting A equals B. Real scalar field then, if already anticipating what this is going to be in the quantum theory, this is an annihilation operator, this is a creation operator, and if they're equal, it simply means that there's no distinction between particles and antiparticles. This is always the case when you deal with a real field. The photon field is real. The photon is its own antiparticle. If it's complex, if you want the field to be different, a particle to be different from its antiparticle, then the field has to be a complex field. So, for example, you talk about the W bosons, the W plus boson, W minus boson are related by complex conjugation. Or later, when these things become operators, then complex conjugation is replaced by taking the Hermitian adjoint. So, of course, you can also invert these formulas, but you can look up the expressions for A of Q in terms of phi of x and phi star of x and the derivative. You can look that up in the books. At this point, we just have to accept that this can be done. So, how should we think of this system? Well, this phi of x, we think of it, as I said, it's the assignment of a field to every point in space and time. So we split this and have a time evolution. The time evolution is given by some Hamiltonian, in this case the free Hamiltonian, and this we do for each point in space. So in some sense what you have here, you have a degree of freedom for each point in space. Now recall in mechanics, if you think about a system of n particles, so this is quantum field theory, and here we're talking about ordinary mechanics of n particles, point particles. We'd be dealing with variables q, I of t. We could put a vector on them, but that doesn't really matter. These are particles that just move in one dimension, n of them, or 3, and if you want them to move in 3 dimensions. So you see now that these particles are labeled by an index I, and now you can think of this thing as being a label too. So here we have a discrete label. And here we have a continuous label. So the idea is now to simply repeat the procedure that takes you from classical mechanics of n particles to the quantum mechanics of n particles, to repeat this procedure for this model, where you have not just a finite number of degrees of freedom or variables, but an infinite number, and a set of variables that labeled by a continuous parameter, and then we simply go through the same steps as we would go on that side. We want to go from the classical to the quantum theory, and this step is called canonical quantization. And this is of course the way this subject was developed historically, first by Heisenberg, Born, and Pauli. Later on there were other ways we now know other ways to quantize, in particular path integral quantization. That came later, but of course these different ways to quantize lead to equivalent theories. So what is canonical quantization? It simply means that I write down a Lagrangian, which in this case is something like 1/2 qi dot squared minus 1/2 m qi squared, I from 1 to n. then I simply define Pi as dl by the Qi dot. As you can see, I put most constants equal to 1, because this is not relevant for what I'm going to say. So in this case, this is just Qi dot. So you now, instead of using Qi and Qi dot, you now use Qi and Pi, the conjugate momentum, and then you simply replace Poisson brackets by quantum commutators, which means that instead of classical variables, you're now dealing with operators. So you simply declare that Pi with Qj should be equal to minus IH bar delta Ij. So then these things are no longer ordinary numbers, but operators in some Hilbert space, as you know very well. Now, we're simply going to repeat this very same procedure for this system. And so, in some sense, this is nothing but the quantization of a system with infinitely many degrees of freedom. That's the only difference in some sense at this stage. Of course, I should say that by going to the Hamiltonian description and singling out the time variable, it seems like we lose Lorentz invariance. And one of the tasks then is that after going through this procedure, which looks like it violates Lorentz invariance, you will have to verify at the end of the day that whatever you calculate, again, satisfies the requirements of relativistic invariance. But at the intermediate steps, now it will look like we're going to lose these invariances. So, well, first of all, I'd have to give a Lagrangian for the scalar field. Well, that's easy enough, or in action, rather. And this will be given by d3x times 1/2 d mu phi minus 1/2 m squared phi squared. So you see that the sum that runs from 1 to n has been replaced by an integral here, and this corresponds to the replacement of the discrete label here by a continuous label there. Well, then we define a canonical momentum, Pt of x is, well, now I have to be a little, I would need to define the analog of a partial derivative for continuous infinity of variables. And there is such an analog, it's called the functional derivative, but I will sort of make it, but sometimes people just put these deltas instead of usual partial differential signs, and I put phi dot to x. So this is the precise analog of this relation, where the label is now continuous, and as you can see, this is just phi dot Tx. So again, you see the only difference at this point is that we've replaced finite number of variables by an infinite number. Well, and then we postulate canonical commutation relations, abbreviated like this. Canonical commutation relations, meaning that we ask that T of x at given time with phi t of y, be equal to minus I h bar. Well, we also have to replace the Kronecker delta, and it has to be replaced by a delta function, delta 3 of x minus y. And in addition, we ask that pi of tx with pi of ty, and same for y, for phi t of x with phi t of y should be equal to 0, corresponding to P with P and Q with Q equals 0. So this is now the fundamentally new thing. We still have this equation here, but now by imposing this requirement, the canonical equal time commutation relation, we've declared this function to be some operator. And of course, we still have to work out what kind of operator it is and what kind of Hilbert space it acts on. But this is the basic step that also in ordinary mechanics takes us to quantum mechanics. And let me repeat, at this point, this is nothing but a postulate. It's you have to see the theory will make some predictions at some point, and then the test is whether these predictions agree with what we see in nature. So at this point, it's simply a postulate. It's simply the transcription of a recipe that worked for classical mechanics to this situation. And as I argued, the only real difference here is that we're dealing with infinitely many variables. But remember, as I said before, we now also have the issue of Lorentz and Poincaré invariance. And at this stage, it looks like this may no longer be there, because we have singled out this time variable and the time derivative, and it seems like we've lost Lorentz invariance. You give me another 3 minutes or so, since we started a little bit late. I hope there are no more announcements tomorrow, because I need every minute. Well, given this, we can now work through all this. In particular, we'll have to use the formulas relating A or expressing A's in terms of phi's. But then you can show that this eventually implies the following relations, namely A, P with A dagger Q equals 2 omega of P delta 3 P minus Q. And what is this? Well, there are others. A with A and A dagger with A dagger are equal to 0. You have a similar set of relations for the B's. Now, this you've seen before. I mean, this is just a harmonic oscillator. If it wasn't for this P and the Q here, if we just had one, it would just be the commutation relations for the annihilation creation operator for the harmonic oscillator. Of course, you wouldn't have this. This number here is a convention. You can define it differently, so you don't have it. You can absorb it into these operators. And here you would have one for the harmonic oscillator, but otherwise it's exactly the same. So we see that these things are creation and annihilation operators, but we have a continuous infinity of them. So we can think of, so phi, the quantum theory of the free fields, the phi describes, in some sense, describes an infinite set of harmonic oscillators labeled by a three-dimensional momentum variable. So for each value of the momentum, we have a harmonic oscillator. And of course, you can also check, you can work out the Hamiltonian and so on. And you can check that, for example, H with A of P is equal to minus omega of P, A of P, and so on. And we also have a relation for A dagger. And what this does tell you, in some sense, that if you apply this operator to some state, then its energy will be lowered by so much. And this is equivalent to removing a particle from it. So this leads us to the notion of Fock space. What is Fock space? Now we can define the Hilbert space. Given all this information, we can define the Hilbert space. and we simply take the definition from what we know about the harmonic oscillator. Now, we can define Hilbert space or Fock space. Well, the first step is to introduce a vacuum state, sometimes written like this, or psi 0. This is the state with nothing in it, which means that A of P is annihilated by all annihilation operators for all P R3. So in classical physics, the vacuum is just nothing. You don't assign it any mathematical expression. In quantum field theory, a vacuum is much, much more complicated. And someone told me that, in the old days in classical mechanics, there was a difficulty solving the three-body problem. It hasn't been solved to this day in some sense. When you go to general relativity, the two-body problem is even unsolved. It becomes more and more difficult. But when you go to quantum mechanics and quantum field theory, it seems like even the no-body problem is not solved. And here in this case, of course, we know, we have an understanding, we can define it, but when we introduce interactions, you know that the vacuum is a highly complicated object. It contains vertical particles and clouds and all kinds of things, and it has a much more complicated structure. Okay, so this is the state, and then you simply build all physics in particle states by acting on this vacuum with n creation operators. Now, sometimes you don't want to localize the momenta sharply, so what you can do is you can smear this with some momentum space wave function, but in this case you get an n-particle state. And this construction is possible for any n, of course, and therefore you now see that you get a description that allows, or you get a description which contains the possibility, or allows for the possibility of having an arbitrary number of particle excitations. So this is something I will discuss in a little more detail tomorrow. So thank you very much.